The angle of incidence of a water wave is 45 degrees. The incident wavelength is 3.5 meters. The angle of refraction is 27 degrees. What is the wavelength on the refracted side? So they're giving us wavelengths and angles. So we're going to pair lambda 1 over lambda 2 with sine theta I over sine theta R. So the refraction equation we're going to use for part A will be this version. Now we're trying to find the wavelength of the refracted wave. So we're trying to find lambda 2. So if I solve it for lambda 2, the first thing I want to do is get it out of the bottom. So I multiply both sides by lambda 2 to do that. And they cancel. And then I can rewrite and start again, get lambda 2 by itself. So to do that, I multiply both sides by sine theta R and then divide both sides by sine theta I. So it ends up becoming lambda 1 sine theta R divided by sine theta I. Now I put in my numbers. My incident wavelength is 3.5 meters. My angle of incidence is 45 degrees. And my angle of refraction, which is on the top of the equation, is 27 degrees. So it should be 3.5 sine 27 divided by sine 45. And when I do that, I get lambda 2 equivalent to 2.25 meters. Now in part B, does this question above represent refraction from deep to shallow or shallow to deep? Well, when you go from deep to shallow, the water will slow down. So that's worth memorizing. And when things slow down, they bunch up. So notice my original wavelength was 3.5 meters. My refracted wavelength was 2.25 meters. So provide two pieces of evidence that confirm it's going from deep to shallow. So first of all, I think it is going from deep to shallow. And one of the reasons is because lambda 1 is greater than lambda 2. In other words, the waves are bunching up. The second reason is looking at the angle. When waves slow down, so if I draw a real quick little diagram here, imagine this is my incoming water wave, like this, coming in at an angle of 45 degrees with respect to the normal. And then when it crosses over the boundary, it goes towards the normal line because the refracted angle is 27 degrees. And if it bends towards, in other words, if the refracted angle is smaller, that again represents a wave that's going from deep to shallow or slowing down. So the second piece of evidence is that theta I is greater than theta R. So those waves must be bending in towards the normal. Part C. If the velocity of the incident wave in the above question was 24 centimeters per second, what would be the new velocity of the refracted wave? So we can pair our wavelengths, because we know them now, to our velocities and write a new equation. Notice we could also pair velocities with angles. It doesn't really matter. Now we have everything. So I'm going to go lambda 1 over lambda 2 is V1 over V2. And we're trying to find V2. So once again, I'm going to multiply both sides by V2 to get it out of the bottom. And I get V2 is equal to, now I want to get lambda 2 out, so I multiply both sides by lambda 2 and divide both sides by lambda 1 to get V2 by itself. So V2 is V1 lambda 2 over lambda 1. So V1 was 24. Lambda 2 was 2.25. We figured that out in part A. And lambda 1 was 3.5. And when I do that, I get V2 is 15.4 centimeters per second. Now, the last one, we'll try and squeeze it in there. See if I can get it in the bottom. I'll do it in blue so we can see it. We're trying to find our frequency. Calculate the frequency of the waves referred to in parts A and C above. Well, frequency, we can use our universal wave equation. V is equal to F lambda. Now, the thing about refraction, the only thing that's consistent from side A to side B when it crosses the boundary is the frequency. The frequency on the incident side is exactly the same as the frequency on the refracted side. They're equivalent. In other words, if 5 waves per second arrive at this boundary, then 5 waves per second must be leaving the boundary, since the incident side is creating the waves on the refracted side. So pick a side and solve for F. So F is going to be V over lambda. So if I use the incident side, F incident should be V incident over lambda incident. And they give you both those. V is 24 and lambda was 3.5. Now notice lambda is in meters and my velocity was in centimeters per second. So I should convert my velocity to match, because ultimately we want to get rid of the meters and have 1 over seconds as my answer. So 24 centimeters per second is 0.24 meters per second. So I'm going to change this top one to 0.24 meters per second. And when I crank that out, I get my frequency as 0.069 hertz. And if I did FR, frequency on the refractive side, I'd get exactly the same answer. In that case, I would pair 15.4, but again, convert that to meters per second with the 2.25, and I'd get the same answer.